effect. Here's the general premise. You've got a piece of metal, and that piece of metal is part of a circuit. And it's an open-ended part of the circuit here. Now this metal is of some variety which has electrons on it, just like all atoms have electrons. You shine on this metal photons. You shine photons, light, photons. And those photons come in with an energy, HF, right? Well, they strike the surface of the metal, and assuming that HF is larger than the work function of the metal, then those electrons will be ejected with some kinetic energy.
Is this where solar power comes from?
It's a little bit of a different process, but yeah, same idea. So the electrons then are shot off of this surface, and they pass to the other plate, thus completing the circuit. So when you have the photons bouncing off of it, you have a completed circuit. So hypothetically, you could power a light bulb with this circuit. I guess it's kind of like that. Or a car. Well, not a car. This is very, very low energy, or low current. So this is basic premise of this is the photoelectric effect. You can generate a current by knocking electrons off of a metal or metallic surface. Now the trick is that you have to have photons of high enough energy. So they've got to be very, very high energy photons. Usually.
So it can't be visible light, it's got to be like gamma rays.
Yes, gamma rays for sure would work. X-rays for sure would work. But usually UV rays work down in the 200 to 300 nanometer wavelengths usually work. Visible light doesn't work with this. And that was what Einstein discovered, that each of these photons carried with it a certain amount of energy based on its color or its frequency. Now, it doesn't matter the intensity, and that's an important thing to note. It doesn't affect the ability to get these photoelectrons. If I take visible light and I just get like 50 visible light lamps and shine them all on there, these photons are not going to get knocked off because it doesn't matter how much light I've got, because the photons from that light aren't energetic enough to knock off the electrons. Just having more light doesn't make the photons more energetic, it just means there's more photons. And it's not the number of photons which is knocking off the electrons, it's the energy of the individual photons. So 50 megawatt lamp is not going to knock off the photoelectrons as well as a 0.1 megawatt or 0.1 watt UV source. Because, go ahead.
Well, 5 megawatt UV light is better than 6. Well, it wasn't 6. It's the same type of light, same frequency.
Yeah. So if you had, say, a 5 megawatt UV source versus a 1 watt UV source, this one will knock off more electrons.
Right.
Or it will knock off electrons at a greater rate because there's more photons present. This one would have fewer photons. These are now, of course, the same energy, but since more photons are coming in with more photons are coming in because it's a higher wattage. So more electrons will end up leaving.
And the electrons, they're on the surface for the protons. Once they interact, the electrons energize. Do they go back through the system? Go back to the end?
Yes. Yeah, the electrons will flow through the system. Now, when you knock off the electrons here, it kind of creates these virtual holes where electrons would like to be. So the electrons flow, and the electrons on this side would then replace those holes.
Right. That drives the.
Yes, you would then have a current at that point. As long as the the photons were energetic enough to knock off the electrons, a current would be maintained in that circuit. Follow? You have to